Okay, let's talk a little bit about the mole concept. What is a mole? Okay, could be the furry critter in your backyard that's tearing up your lawn. Not in this case. In science, there was a need to be able to express very, very small measurements and very, very large measurements in an understandable, workable number that you could put on a piece of paper and use it in conversion factors and do calculations with it. So, scientists had to come up with a standard. And they did, and they called it the mole. Let me explain a little bit about what the mole is. A mole is simply a reference to be able to take very small things, like atoms of hydrogen, for instance, or very, very large things, like the number of molecules of water in a gallon of water. That's a lot of molecules. It's trillions and trillions of molecules of H2O in a gallon of water. How could you put either of those two on a piece of paper and start doing calculations with it? That's where the mole comes in. So the mole really works two ways. It's twofold. It allows us to take really small, like elements, atoms of elements, which you can't see with the naked eye. You have to have an electron microscope to see these atoms. So how on earth can we figure out how to weigh those out in, let's say, NaCl, sodium chloride? How would you be able to put that into something that we can understand? Simple. Let's take NaCl as an example. Okay, we know that sodium, the atomic number, is 11. What does that mean? It has 11 protons, 11 electrons, and if we subtract 11 from the atomic mass, which is 22.98 rounded up to 23, we find out that it has 12 neutrons, which have no charge. And we know that protons and neutrons are what create all of the mass of an element. They're centrally located in the nucleus, very tightly compacted. They are what provides all of the mass in an element in one atom of sodium. So, how would we weigh out sodium, because we can't even see an atom of sodium? Well, what the science world did was they took the 22.98, which is the atomic mass of an element, and you weigh it out in grams. So you put a gram behind every atomic mass on the entire periodic table, and what you're going to have is 1 mole of that element. So for instance, 1 mole, and you just have to write MOL, of sodium is equal to 22.98 grams of sodium. So what we've done is taken something so microscopic you can't see it with the naked eye, put a gram symbol behind the atomic mass, and called that 1 mole. And every element on the entire periodic table works exactly the same way. So you may hear the term molar mass. Let's talk about molar mass. This is the molar mass of sodium, 22.98 grams. What if you needed to know the molar mass of sodium chloride? Okay, what do we have to do? We have to look at the chart. We have to get the atomic mass for sodium, which is 22.98. And then we have to get the atomic mass for chlorine, which is 35.45. So how do we get the atomic mass, the molar mass of sodium chloride, we add these two together. So, 1 mole of NaCl is equal to, second, should have my calculator ready. Okay, so let's see, 22.98, 35.45, 58.43 grams of NaCl, sodium chloride. Okay, so we've established a constant relationship between the molar mass of all elements on the periodic table and also those elements used in compounds like sodium chloride, for instance. You add the total atomic mass of each atom in there, in that particular compound or molecule or whatever it is we're talking about. That gives you 58.43 grams. That is the collective molar mass of NaCl. This is very important because you'll be using this probably for the rest of the semester. Okay, so now that we know how to figure out the molar mass of a compound, a simple compound, let's talk about figuring out the molar mass of something a little more complex that's got a few more elements to it. Let's take excuse me, I have a cold. I've been fighting one. The family's been passing this back and forth for about 2 months now. I'm ready for spring to get here. Okay, so let's talk about the molar mass of something a little bit more complex. Let's talk about something that we will have to, okay, so PO4. We know that is phosphate. So how would you figure the molar mass of phosphate? Okay, what you do, you figure out how many atoms of phosphate you have, of phosphorus. You have 1, right? How many atoms of oxygen do you have? 4. Okay, so let's get the atomic mass of each of those elements. So 30.97 for phosphate. Remember, we're just taking the atomic mass and putting a gram symbol at the end of it. Gotta get my calculator for this one. Oxygen. Some say 15.999. Most instructors, including Mr. Williams, use 16. Okay? So you have 4 oxygen atoms at 16 grams. So that's 16 times 4 equals 64 plus 30.97 for a grand total of 94.97. So now, let's write the conversion vector that we just created. So 1 mole of phosphate is equal to 94.97 grams of phosphate. Okay, all we've done, taken information directly from the periodic table of elements, added the grams to it to make it a workable number that we can understand, and then done the calculations for each atom of each element involved in that particular compound, in this case phosphate. Okay, so let's talk about something that's a little bit more complicated and tends to blow everybody's mind when we start talking about mole from the other direction. That's an example of how you can use the mole to take really small things like atoms and molecules of compounds like water and phosphate and be able to figure out what they would weigh on a balance, like if you were mixing in an experiment in a lab. I'm sure you all had to do that already. So that's how we came up with the concept to go from small to understand. Well, let's talk about how you get from the other end, large. There's an important number you have to know, and it's called Avogadros number. And it is 6.02 times 10 to the 23rd power. That's about a trillion. So a number that for us as humans, you know, we can't really fathom. But believe it or not, let's take H2O, water molecule, right? We've all seen this diagram. One molecule of water. 6.02 times 10 to the 23rd molecules of water would be about maybe an ounce, you know, a couple of sips. So we're talking really small units in very large quantities. So we had to have a way to understand those large quantities, and we use Avogadros number to help facilitate that. Okay, so let's take it one step further. By the way, Avogadros number and the mole, you're going to see in a minute, are going to work hand in hand. So the mole doesn't have to apply to just elements. It can apply to molecules. It can apply to compounds. It can apply to this marker I'm holding. If I say that I've got Avogadros number of this marker, that means that there are 6.02 times 10 to the 23rd of these markers, which would probably be enough to fill up this entire building. Okay? So this is just a way of taking anything, any unit, any element, any compound, in a really large volume and making it understandable. So let's do something a little bit more practical, see if we can understand how this all comes together. Okay. So let's talk about water. Okay, so we know, let's break down H2O. Let's figure the molar mass of water. Molar mass of H2O. Okay, what do we have in H2O? We have two hydrogen atoms, right? And they are each 1.01 grams in their molar mass. Okay, and then we've got one oxygen, which is 16 grams. So you've got two 1.01s and a 16. That's a grand total of 18.02. So we can now say that the molar mass of one molecule of water, or the molar mass of water, the molar mass of water, of the compound water, is 18.02 grams. So we can now say that 1 mole of H2O is equal to 18.02 grams of H2O laid out on a balance. So when we say 1 mole, that also, it's synonymous with the molar mass. Okay, so we got the molar mass of water figured out. Now, let's create another conversion factor. Okay, 1 mole of H2O is going to be equal to Avogadros number of water molecules. Okay? You look at this thing as one separate entity. Okay? We're talking about 1 molecule of water. And then we consider 1 mole of water, like a jug of water or whatever, for instance, or a cup of water. So we're talking about collective number of water molecules to form enough water to weigh out 18.02 grams. That's your mole of water. Okay, so 1 mole of H2O is equal to 6.02 times 10 to the 23rd molecules of H2O. How do we know this? Did somebody take 6.032 times 10 to the 23rd molecules of water and count them out and make sure that it weighed 18.02 grams? No, of course not. Don't worry about it. Leave that to the physics people, okay? They're the people that look at everything with scanning electron microscopes and look at all the different various properties and estimate their weight. There's probably a pretty good margin of error in that, but understand that it's not, you don't have to worry about that part. It's just a standard that we use. Everybody in the scientific community agrees upon the fact that 1 mole of water weighs 18.02 grams, and 1 mole of water also has 6.02 times 10 to the 23rd molecules of H2O to comprise it. Okay, now there's one more. Let's take this one step further. Now let's start breaking it down. Okay, so in 1 mole of water, let's suppose we wanted to know how many moles of hydrogen were in 1 mole of water. Okay, well let's look at the compound water again. Okay, H2O. That means we have 2 hydrogens and 1 oxygen, right? Okay, so for every molecule of water, you're going to have 2 hydrogens and 1 oxygen atom. So what we're going to do, we can take that information, the quantities in this molecular formula, and we can create relationships between individual elements and the entire compound. So, based on that, 1 mole of H2O is going to contain 2 moles of hydrogen. Okay? Why is that? Because there are 2 hydrogens in every molecule of H2O. Okay, so that's just a simple, basically look at the quantities involved in there. Let's take a different one, for instance. Let's try magnesium chloride. MgCl. We have to have a 2 here, right? Because magnesium is a 2 plus, chlorine is a 1 minus. So ionic compounds always have to equal 0 when you balance out their charges. So that would be MgCl2, magnesium chloride. Let's look at the molar relationship of each of those individual elements with regards to magnesium chloride. So 1 mole of magnesium chloride is going to equal, let's look at how many elements we have of each. How many magnesiums do we have in a magnesium chloride? 1. How many chlorines do we have? 2. So, in 1 mole of magnesium chloride, there are 2 moles of chlorine and there is 1 mole of magnesium. How did we get that? We just looked at the quantities of each atom in the compound. Okay, so that's a start on moles. You're going to find out it gets a little bit more complicated than that. In balancing chemical equations, you're going to be looking at these ratios and these relationships of quantity pretty much all the time. But what you just have to remember, 1 mole of anything equals 6.02 times 10 to the 23rd of that object or compound or atom, whatever it is. Now when we talk molar mass, 1 mole let's change this around. Let's say we want to know what 1 mole of sulfur is equal to. Well, how do we do that? Simple. We go to the chart. We see that sulfur has an atomic mass of 32.07, and it's just basically taking information off the chart. So 32.07 expressed in grams. So 1 mole of sulfur is equal to 32.07 grams of sulfur. That's how you calculate the molar mass. Let's do what we did over here with water. Let's do that with just a single element of sulfur. So 1 mole of sulfur, which we know weighs 32.07 grams, if you were to have a container of sulfur, put it on the balance, measure out 32.07 grams, you would have exactly 1 mole of sulfur. How many molecules, how many atoms of sulfur are in 1 mole of sulfur? Avogadros number, 6.02 times 10 to the 23rd atoms of sulfur. So you can see how the mole and Avogadros number work hand in hand. They're synonymous. They're equal to each other in some respects. And they are going to have to be interchangeable in the conversion factors that you do as time goes on.